Next speaker, Dr. Sunil Manna. He is scientist 7, Center for DNA Fingerprinting and Diagnostics, CDFT, Hyderabad. And Dr. Sunil did his PhD from IISc Kolkata, postdoc from MD Anderson Cancer Center. He is also top 2% biological scientist according to Stanford University ranking, recipient of Scopas Young Scientist Award, Fellow of National Academy of Science, and recipient of National Bioscience Award. Area of interest, molecular events of inflammatory disease and possible therapeutic intervention. And Dr. Sunil is going to talk on the role of advanced glycation in product in exerting advanced effect and its regulation. Dr. Sunil, please.
Good afternoon. First of all, I thank the organizer, especially Professor Bharti and Manju. Of course, the overseas Professor Arada Agarwal is not. So my topics of talk actually role of advanced glycation in products in exerting adverse effects and its regulation. So I don't know how many people you know the age advanced glycation in product. So basically age is just when you are taking a lot of sugars or in the diabetic condition or aged person where metabolic activity is not that much, you cannot break that. So high level of glucose, normal system actually becomes tricarbon sugar, and these are like a methyl glycol, one of them. So these are sugar derivatives, and this non-enzymatically entangle with the protein or fat. Okay, so that actually results the formation of the whatever the products, either protein or fat, that becomes named as advanced glycation end products. So we are looking actually this. Normally in the body that have formed like that way, but in case of when you are taking the food, especially this, the browning effect of the food happens because of this. So mostly the reaction happened like Amadori reaction, this Maillard reaction, means that is the browning effect. That actually makes the basically you are barbecue the products that become brown. So there are a lot of actually advanced glycation in products would be there. So that's why careful to take those actually products, those who have the diabetic or the aged. So here actually a lot of listed products are there. So whatever the 3 carbon sugar moieties that used to entangle in the protein, I used to tell mostly. So here the structure of those, just going into that. And most actually damaging effect happen when, see, if it is a short-lived protein, so they used to degrade and just bypass. But if it is a long-lived protein like length crystalline, or a lot of proteins in the heart like tendons, ligaments and cartilage, collagens. So there, that time a lot of effects would be there. So normally actually when this kind of collagens becomes glycated, that time the tissue becomes rigid. So especially in the heart muscle, it cannot move that way you will get the effect. So here a lot of actually listed diseases are there that are involved through the age. And age actually acts to its specific receptor called RAGE, receptor for advanced glycation end products. And it has different forms listed here, and which are the cytoplasmic domain. So if it is the cytoplasmic domain, then it used to do the signaling cascade, it used to follow the signaling cascade. And if it is just, you don't have the cytoplasmic thread, then they are just becomes like a soluble. Lot of times this soluble is used to as a therapeutics, but some it did not work as a therapeutics for other reasons. But normally we are interested where these C-terminal domains are there, where a lot of signal transduction happen, and that leads to several deleterious effects. And I will come one by one those effects, how it is doing, how we can regulate. So these are actually different cell signaling cascade already known, and mostly it is doing the, it induces reactive oxygen that leads to stress responsive transcription factor activation like NF-kappa B, and other some pathways are also there like reactive oxygen like inos also activating. So this is known to report. So for the research purpose, we prepared the age using the human serum albumin. Human serum albumin is inert protein which have no effect except the tonicity in the blood, and we actually incorporated age by like same non-enzymatic. If you incubate the age with the say for 7 days, then it will make the HSA MGO. We used MGO as a tricarbon sugar actually for to make the age, and biochemically we measure that how much molecules are entangled, like 31% proteins are entangled with this methyl glycol. So whatever we are using, if it is 100 microgram of age or HSMG we are putting, basically that is 31%. Okay, and this is actually, if you incubate this, it will give you this browning effect. In this test tube actually it is showing, and which actually amino acids side groups it is entangled. It is just going through that. If you are interested, you can go through that. Okay. Then we find out that we use different like methyl glycol, D-glucose, glycoldehyde, ribose. Then we find out to activate. See, our actually activation is NF-kappa B activation we are looking, and we find out the methyl glycol main age is the most effective age, which is shown by gel shift assay, NF-kappa B activation as well as reporter gene activation. And in terms of deleterious effect, we use the cell and find out that it is giving almost 32% cell death. It is not huge, but it is very slow reacting, slow acting. That's why it is giving just 32%, but that is enough for the inducing the lot of neurodegenerative diseases, which is the age-old disease. And in terms of apoptosis is multiplying, we improve like a caspase activation and other things. And if you look actually NF-kappa B activation, which have role actually we used to tell it has proliferative effect. But in case of proliferative retinopathy, there also it is it is self-proliferating. But in most of the cases you have to regulate actually this NF-kappa B to regulate this action. And we find out not only the NF-kappa B, it is also activating AP1, NF-80, okay, and whatever actually NF-kappa is by activating kappa B alpha degradation. Because see here we want to look that how it is doing the apoptosis. Okay, so to know the mechanism, we check this transcription factors activation. But here actually AP1, NF-kappa B, NF-80 activating, NF-kappa B is known. Then we looked actually whatever dependent gene for these transcription factors. But also we got it increases the different proteolytic enzyme activation, because as it is a receptor ligand mediated action, so it is inducing some of the proteases, myeloperoxidase alkaline, that means it is helping in the degranulation. So when receptor ligand interaction, so it induces degranulation. And degranulation in that product, we find out interleukin 8 actually it increases the level, which is shown in the supernatant, and which reverse effect in the palate. So that means supernatant IL is secreting. Okay, so this because of the ILA, and we find out that a reactive oxygen and all actually activation is going on, and antioxidant, what it is reported, it is acts through activation of the reactive oxygen. That's why we use several antioxidant that is blocking. Okay, that reactive oxygen. This is known fact. So and as calcium is increasing. As actually interleukin is increasing the level by degranulation, we find out it increases the intracellular calcium level, which is shown by the in this actually figure, that age increases calcium level, and because of the calcium it also increases the calcinuric, one of the phosphatase activation, and it also increases NF-80 transcription factors, which remains in the cytoplasm in the phosphorylated forms, and when it is dephosphorylated it is to transfer it to the nucleus. So now this NF-80 dependent luciferase gene activation as well as we also looked actually several other like jet shift as and other way. And NF80, when it transferred it to the nucleus, because of the dephosphorylation by calcineurin, so NF80 dependent gene is the first ligand. This first ligand expression you can see as per the Western blot. Okay, and first ligand dependent gene expression. So like that. So AG-RAG interaction leads to intercellular calcium release, followed by calcium reactivation. NF80 phospho becomes non-phospho. That's why transferred to nucleus and dependent gene first ligand expression. And if you put that here, actually we used anti-IL8 antibody, anti-TNF antibody, but find out that anti-IL8 antibody, if you use, that is actually that basically blocks this effect. Okay, in this jet shift assay, whatever actually see, if you block the calcium or anti-IL8 antibody, so whatever this NF-kappa B activation by age is blocked, and the first ligand expression again, why it is also blocked by either blocking the calcium receptor 2N, the chelating agent, or by anti-IL8 antibody, but not the TNF antibody. TNF also very strong in user of NF-kappa, that is not affected, but IL8 dependent action is affected. So that's why we are actually, and here it is also telling that same thing, the apoptosis assay. So in this actually cartoon, whatever we are telling, AG-RAG interaction leads to the degranulation of the several things along with that, like protease lytic enzyme as well as the IL8. That IL8 increases the intercellular calcium, and that calcium leads to the calcium activity, NF80 translocation, followed by the first ligand. That's why it is inducing cell death, especially the neuronal cell death. And age increases reactive oxygen because some actually reverse, either it is increasing the reactive oxygen in our system is not. That's why we use this one. And I'm just passing. And now actually another deleterious effect like a diabetic response. So normally diabetic response is the lot of the glutathione compounds which is activating the PPR gamma, that is acts as a anti-diabetic drug. Normally what it is doing, this troglytathione increases the PPR gamma DNA binding activity, and if you increases incubate with the age followed by troglytathione induction, the PPR gamma down regulation happened actually because of the age. And this PPR gamma dependent APM, AP2 also decrease. And here actually NF-kappa B and PPR gamma have the inverse role. Just I will pass that on. But here actually the important findings here. See, if you put antioxidant, this PPR gamma, okay, down regulation, basically antioxidant cannot protect except the mangiferin. That's why coming to the actually our point that antioxidant mangiferin protects age-mediated PPR gamma down regulation, but not other antioxidant. That means whatever antioxidant activity is not actually whatever may be shown by the mangiferin, but mangiferin is showing something other. Mangiferin is derived from a mango, that is also true. And to our surprise, when you incubate this mangiferin with the just your in the test tube with your nuclear extract, different concentration of nuclear extract, it is increasing the DNA binding as such in the test tube. That means in vitro. That means the compound directly having some, basically it is enhancing the binding of PPR gamma DNA binding activity. Okay, and it is actually in silico also you just put that one, that the PPR gamma and troglytathione and mangiferin binding. Okay, and whatever the free energy calculation also finding that it is also looks like a troglytathione which is known inhibitors of this known activator of PPR gamma. Okay, so that's why we are telling you, because just I did not put so much data, actually we already published those data. That's why actually it is increasing the diabetic response by mangiferin. And now I will go actually that age increases lipogenesis. That means age, advanced glycation in products in the diabetic condition where high level of they are always obese, actually obesity is to come to the picture. So how it is doing in terms of mechanism, whatever actually age increases along with the concentration, it increases the lipogenesis, means the lipid droplets are forming here. It is shown in this actually staining. And
Dr. Sunil, you have 5 more minutes.
Okay. So whatever actually this basically the transcription factor SRBP, it is activating SRBP along with the other transcription factors, and antioxidant basically blocking this other transcription factor like AP1 NF to a part of not the SRBP, but mangiferin is blocking this SRBP, see, induced by this age. That actually surprises how mangiferin is doing several effects. So I just pass quickly these things. So that's why maybe we are telling maybe mangiferin has the huge potent role to down-regulate the SRBP that leads to the decrease of the lipogenesis. And what we find out, this age-age interaction leads to the autophagic action, and this autophagy is the prolonged autophagy what we are finding out, and prolonged means it is impaired autophagy as per our whatever I will come to that. So age basically increases the autophagy here, and this autophagy actually, that age increases autophagy and lipogenesis both, but when we use this glucose, which is known inducer of autophagy, that is normally it increases autophagy followed by the maturation leads to the autophagy coming down in this towards end, but not the in case of the age. That's why telling that prolonged autophagy, all biochemical marker and other things we already proved that one, that I am not showing here. So that increases autophagy, and that is prolonged autophagy. Whatever this cartoon we showed in this journal JPC, that age-age interaction leads to several signaling cascade, actually that all of you have the evidence or data, but I cannot bring that one. It increases several transcription factors along with the SRBP, and that leads to the increase actually lipogenesis. And this see, what we find out is mangiferin has a huge role in different actually functions related to the age-mediated functions. So now, really we can use this mangiferin as a therapeutics, and we find out this mangiferin is a very good inducer or activates catalase activity, and here actually multiple way we prove that on the catalase activity is going, and the well-known the catalase activator is amino triazole ATZ, and we find out that this mangiferin in silico, whatever we find out, the mangiferin and ATZ are working in two distinct sites, they have the activity. So together maybe that will be good for the catalase blocking that way. And so I pass this now. And binding energy, other things we already calculated for this. And this mangiferin actually, with the structure of this mangiferin, it looks like that way. Mangiferin is derived from the mango, that is I think already known. And this is the different structure, a lot of hydroxyl groups are there. And this structure, whatever it follows, if you go for therapeutics, you have to look actually several of these by the property like molecular weight less than 500, lipophilicity and hydrogen bonds. All those things actually, these are Lipinski's rule here. So that might actually follow. That's why we are actually pushing this compound as a therapeutics, as it is in the age increases the diabetic response or obesity, impaired autophagy or neurodegeneration or aging, like that way. So that's why we are thinking to move actually that way. And some of the preliminary data already we have. I am not presenting that one. How it is, especially the obesity one we are working in vivo model. Maybe next I will present that one. Although we don't have that much data right now, so I am not bringing that one. So now actually this already advanced glycation input has the role in inflammation, apoptosis, that is mostly neurodegeneration, impaired autophagy, that's why maybe doing the cell death, and diabetic response and obesity, that is lipogenesis. Okay, and maybe mangiferin go for the therapeutic this action. So and this Sapuraga or whatever the concept of the Indian herbals, maybe mangiferin might follow like that way. So that way I'll stop here. Just I will acknowledge the students last 10 years, whatever actually this work actually done by the students. These 5 students are worked actually in this language, and the Safis are who is still working in this angle. Basically, she is now working in the AKRP in the obesity model, and role of the age in that angle she is working. And I will stop maybe there.
Thank you, Dr. Sunil. Any question? Yeah, Dr.
Dr. Sunil, it's a very nice presentation. I have one quick question. AGE, it can increase diabetic property as well as the lipogenesis. So how you have measured that AGE can increase the lipogenesis? Which model you have used, and what are the marker you have checked other than what is called lipid droplet study?
So in the condition in the cell-based assay or
Yeah, cell-based or any animal model.
see while doing staining whatever I showed you, okay, that is mostly the staining for the lipid droplets there. Now we are measuring in the super resolution microscope how many droplets are there. That way computerized actually will tell how many.
Is there any lipogenesis marker you have checked?
See, the SRBP the transcription factor.
SRBP is for actually cholesterol pathway or maybe fatty acid pathway, but other like surface marker like CD36,
We did not look
like
those
leptin, adiponectin, that type of thing.
did not look actually those markers, but only just
Okay.
inside cell whatever SRBP and we didn't like it. All those actually we already showed.
Thank you.
Hi Dr. Manna, nice talk. I have a question. 3 hours to 5 hours, biologically how you can say that is and because as you see like as the Western you have shown, yes multiple but some of them that effect is gone in fact when you went to the 6 hours or whatever it is. So the fundamental question is, the whole idea is about the biological aging. So how you can suggest 3 and 6 hours biological aging and how you can correlate the, because whole thing is depending on that. So can you please comment?
So means you are telling which the lipogenesis of which experiment?
No, the whole story. The point is, it is a 48 hours, 62, the few hours or the 3 days as I conceive it. Because some of them, number one, the effect is gone. It doesn't matter. All the things they need not to match. But in spite of that,
See,
it's a biological aging. How you can correlate this?
Any support stimulus, immediately it will induce the support reactive support TNA or any actually like that. Here we are using it, which is a little bit slow. Support TNA. It induces within minutes actually a lot of signaling, but it takes its dependent gene to activate support 12 hours. Support TNF induces NF kappa in 30 minutes to 1 hour started. But depending on you will get like a 12 hours or overnight like that. Same way it is.
You are very true. That can happen with any kind, So, but the question is, still the original question, my concern remains. What you said is true. That can be, any kind of stimulus. Having said that, how you can correlate when you say, because whole story is about the aging, how you can correlate 3 days and the 6th days with reference to the age, because whole thing we are living neurodegeneration and cancer, right? Yeah.
Receptor ligand interaction. So when it is action is there, cytoplasm, a lot of factors is recruited. Okay? This recruitment of the whatever factors followed by kinases coming to that milieu. Okay? Some receptors are very slow. So when ligand might say for
I'm sorry, that is not my question. My question is very simple. 3 hours or 3 days or 6 days, whatever it is, how you can...
Maybe we can discuss during the tea break.
No problem.
We'll have tea break soon.
basically apoptosis you have to go for long.
We are running late.
Only you can go for less time.
Okay, thank you very much, Dr. Sunil.